Okay, guys, welcome back. It's the last lecture for the first week. That's where we stopped yesterday. We stop at the stage where we come to this. What's happening here? That's where we stopped yesterday. It's a result which says that's the one which connects our new definition of the limit with the old simplistic definition. I promise you the proof. It's a beautiful proof. But that's why I kept it for today. We'll just look into that. Yeah. Did I open it? Yeah, this is the one, sequence limit by components. So that's the theorem we're looking at. Again, we have two sequences. We have one sequence, xn, and the limiting point x. Each of them I gave names to components of. Here the components of xn sequence. Here's the components of x, limiting point. Here I need two indices. Just pay attention again. M, Mary, stands for the dimension index. N, Nicholas, stands for the sequence index. So the theorem says, rather than computing the limit of a sequence, you can compute the limit of components, and that is the equivalent things. We'll just see what I have to say proof-wise. Okay. First we go forward proof. You right, guys? Okay. So we take this definition of a limit, and we use one of the results we established yesterday. We're going to restate this in terms of the distance sequence. So we say this one implies that the limit of a distance sequence is 0. And you see, I'm choosing the particular choice of a metric, d infinity metric, not Euclidean one, because d infinity is better here. It works better. And we can do that because, remember, yesterday we established that limits, the way we define them, they're independent of a metric which is used in the definition. And it's my choice right now of using d infinity. Now, look what it says. It tells me. D infinity, I'm just reminding you what d infinity is. That's how we compute the d infinity. It's a max of a difference of components. Components of xn sequence, they are right here. Components of x sequence, they are right here. And altogether we have m components, m for Mary. Now, because max, that's the nature of max, it always dominates the component, the actual values which produce the max. So I can say this. Each individual difference, it is controlled by the max. It is controlled by the d infinity number. That's the nature of max. And look what we're having now. We're having sandwich principle, isn't it? Remember, in the theorem, our objective, if we go forward, implication, our objective to establish these limits. These are numerical limits. So if I use sandwich principle, the right-hand side of this inequality vanishes, right here. Left-hand side is simply 0. By sandwich principle, I can say that the limits of these absolute values of individual differences, 0. For every k, 1, 2, and m, which is equivalent to just saying that the limit of components xk n's is just xk. And we finished our forward implication. We started with this side, and we concluded this side. I told you I love this proof because you see how beautifully we use, how in a smart way we use these metrics things, our equivalence theorems from yesterday. We chose a particular metric which was useful, which was helpful here, and we use that to our advantage. Let's just see what I have to say in relation to the reverse implication. So we start now with the individual components of the limit. So now we're assuming that components are converging individually. Again, I'm going to choose a metric, but this time, different metric. Look at this. Well, first I interpret this in terms of the absolute value, so I'm just making this step backwards, this step again. For every k from 1 to an m. Now look what I'm going to do. I'm going to use D1 metric. It's now the extreme metric. There was infinity on one side. Now I'm going to use the D1. It's not the extreme of my family of metrics. Look at this. D1 is just, if you remember the definition, there was p there, but when p is 1, it's just sum of the absolute values. As simple as this. It's a D1 metric. Now what can I say now about the D1 metric? Because I have this, and that is true for every k from 1 to m. If I have a sum of vanishing sequences, each of this absolute value as a sequence with respect to n, it's a vanishing sequence of positive numbers. If you have a sum of vanishing sequences of positive numbers, is a sum with m for merit components, this sum will also vanish because every individual summand in your sum is vanishing. So from here, from this one, and from the formula for the D1 metric, I can say that the limit of D1 metrics is vanishing. But now if I use this interpretation of limits of vector limits of vector sequences in terms of the metric, I can say because it's independent of a metric, so I can use the D1 metric this time. I can say that the limit of xn sequences as vector sequence is x, basing on my D1 metric. And that finishes the opposite implication. That's, by the way, one of the examples, one of these rare examples where forward and reverse implication, they require substantially different arguments. Unlike the examples we saw before, where reversal chain of implications was almost identical to the forward chain of implications. Here, it's a substantially different. We need a different metric, unlike the forward one. It's a nice piece of a proof. As a matter of fact, all we did yesterday, originally I planned it just to show you this proof, because this is a very beautiful piece of mathematics. Very non-trivial, especially if you come up with this on your own. If you can do something like this, you can be really proud of yourself. It's a good one. Any questions? Okay. Well, that's all we have to do. We have in relation to limits of sequences. And now I have a little bit to discuss about the limits of functions as opposed to sequences. This already will be building upon our knowledge of limits of sequences to some extent. So let's just go back to that. I go back to my main slides. Definition of a limit of a function. This time we're looking at the vector function, so the function which has multiple arguments and multiple values, sort of. Multiple values, it's not really a good way to say it. Function has a single value all the time, but the value is a vector, so it's a m tuple of numbers. The definition formally, it will be just epsilon-delta definition. That's how it goes. For every positive epsilon, you have to be able, and that's the actual content of justification of a limit. You have to be able to present a delta, positive, such that if your x falls within the delta ball with respect to Euclidean metric of the point A, then f of x, the image of point x, should be within the epsilon distance, within the epsilon ball of the point B, limiting point. This time, you see, well, that's what I told you yesterday, actually. The material is going to grow up, and we no longer will be able to discuss every particular definition and proof in such detail as we discuss limits of sequences. But on the other hand, they're all very similar. For instance, here, we could define limits with respect to different metrics. Not just Euclidean metric, like it is done here, but any other metric, delta, like I did with the limits of sequences. And with some effort, we can establish that all those limits will be equivalent, especially when we talk about DP metrics. I'm not going to do it, because after we've done it for limits, you can at least trust me that it will be similar for functions. Mathematically, it no longer represents any challenge, because all of the key ideas we saw when we did things for sequences. And that's why we're not wasting time on this. We don't have that much time. But in principle, this can be done. And in principle, we should remember this, that limits, in principle, can be defined for any other metric. And similarly to what happened with the sequences, they will be equivalent all the time. But I do it for the Euclidean method. See, G, no index or anything. This is just alternative line. Not in, it's written not in terms of the distances, but in terms of the balls. Actually, I said it on the slide. Oh. Similar to limit sequences, this diff can be blah, blah, blah. Well, from last year, Jonathan Kress put this like a demonstration of this definition. Again, limits, you can say what the limits are in a plain English, like with the sequences, and it's a part of the skill of being a mathematician, or part of the claim that I know mathematics or I know the analysis. It's a skill which, the skill is that being able to put the, convert the Epsilon-delta definition into the plain English and vice versa. Let's just look at the demonstration. Where is the J. Kress? It's the same definition. So what does it show? It shows you, basically just demonstration of a definition says this: no matter how small you take the neighborhood of your point B, of the point which is claimed to be the limit of the function, no matter how small you take the ball around that point, there will always be a corresponding ball around the point A, the point where x is going to, such that every point within this red ball goes into every point within the blue ball. So every point here goes into the point here. Yeah. You can make this ball, if you make this green one smaller, there will still be some choice of red one, even smaller one, but still there will be a choice, such that the same thing happens. So in the formal presentation, that's the part of the presentation, convince everyone that no matter how small you make the green one, you will be able to find the red one over here. I have one example, I think. Yes, I think I have one example where I show you how you can do that. Yeah, I have one example here. Here it is. This is the function. It's a little bit artificial, but still, why not? Good function. It is a function of two variables with values in R. A little bit simplistic setup. In our definition works for functions which take values in vectors and which lives on vectors, but this time we just take from two-dimensional vectors to R, with one exception, with the 0 point. This dot's supposed to be comma. Oh, I just make a note. I want to fix that. So we claim that the limit is 1. We can check that. Look at this, how we check that. We compute the distance from f value to point 1, the value of the claimed limit. That's the distance. Because it's in numbers, the Euclidean distance is just simply absolute value of a difference. Here it is. Well, some arithmetic done is here within this absolute value. This x squared plus y squared is lifted to the numerator. It cancels these two terms. That's what you end up with. Now we also compute the distance in the domain between xy point and the 0 point. That's how it is. Now we make this observation. We'll make this observation that if we take this expression, which represents the distance for f and 1, if we throw extra term in the numerator of this type, and being able to come up with this idea of introducing this extra term, it's a skill which you can pick up from different examples. You can only learn this skill by practicing and looking at how other people do other examples. It's the first time you see something, and it's a good thing to remember. Because if I throw this extra term, It's a positive one, so that will make my fraction larger. That's why I put the inequality here. And I throw this for the sole purpose, because if I throw it in, this becomes a perfect square, and I can abbreviate it to something like this. And I can cancel my fraction into single expression like this. That was the only purpose of introducing this extra term, to make it look like this, to make it linked to my distance in the xy plane. Because now it's just a square of the distance in xy plane. And so now I can convince you that for every positive epsilon, no matter how small that epsilon could be, I can produce a choice for delta. This is the very explicit choice for that delta, which works all the time, no matter how small the epsilon is. The actual content is this presentation of delta. This delta works all the time, because look at this. As soon as the distance from xy to 0 is less than delta, via this inequality, the distance from f to 1 will be less than epsilon. Presenting delta as the content of the proof. And all the time, no matter what, all the time, the justification for this presentation will be some sort of inequality. On this occasion, is this inequality. Analysis, like it or not, it's about inequalities, about being able to find proper inequality from your head, from the record of known inequalities, from your intuition, and being able to put this inequality in the right place. The rest is just beautiful wording around it. That's the beautiful inequality which works here. And that's all there is to it. Is that right? Yes, that's all there is to it. Any questions? Okay. If there's no any questions, I go back to my main slides. Now, there's a little theorem which connects limits of functions with limits of sequences, something we know a lot better than limits of functions, because we just studied this in a lot deeper. We spent the whole lecture yesterday and a little bit of today on sequences. Here's a connection. Look at this. It says that if you have a function, k variables in the domain, m variables in the codomain, and you have a limit claim of this type, then this is true if and only if, look what happens. If and only if for any sequence of points converging to A in the way we introduced yesterday, the sequence f of xn, that's another sequence of vector points, even though in a different space, in the space Rm, converges to B. So on many occasions, when you check or prove that limit of something, well, most of the time actually it's to disproving. It works very nice to disprove something. For instance, if you want to disprove that something like this is not true, then finding a sequence for which this fails, it's a very good way to do it. I'll show you one example a bit later. Yeah. I'll show you the proof for this. Just wait a sec. Do I have a proof for this? What looks confusing to you?
If and only if. What does that mean?
It means that if the limit of the function is b when x approaches a, then whenever you take any sequence approaching a, f of that sequence, which is another sequence in its turn, will approach b. And vice versa. Well, the opposite one is a bit harder to visualize, or to maybe understand, but it sounds like this. Well, it just tells you, if you want to conclude this by using sequences, you have to test this on every sequence. So, as a matter of fact, implication from down to up, from bottom up, sorry, it's not really often used, because how could you possibly physically check for every possible sequence? There are millions of them, infinitely many choices of sequences approaching A. So you can't possibly check it for every sequence, like manually taking sequence, checking, taking another one, and checking. So from bottom-up implication, even though it's true, it's really, well, not so often used. But from top-down, it is used very often. For instance, like I said, in disproving that the top statement is true, you can disprove it by just finding one sequence which violates this. There will be examples later. I'll show you how we do this. That's all right. Yeah, actually I want to show you the proof. It's a good proof, another one. Function sequence limits equivalence theorem. Here it is. Yeah. I think it's one of the last ones. I mean, when we have the opportunity to look at the really beautiful, formally written mathematical proof with all details. Maybe not. Well, doesn't matter. Right. Forward one. Forward one is easy, relatively easy. So we're just assuming this. And we would like to conclude this for every possible converging sequence. Well, that's a very good piece of the epsilon-delta type argument. So I fix a positive epsilon. Given that we're assuming this is true, I can now just do the expansion using the definition of the limit. What does it say? It says this. Limit of f of x equal b, by definition, implies that there is delta, positive delta, such that every x within the delta distance of a point, every x within the delta distance of a point implies that f of x point will be within the epsilon distance of a b point. It's just a legit, it's just expansion of the definition of the limit. Now, I fix a sequence, xn, like this. So I fix a sequence which converging to A. And now I do the expansion for this limit, for the definition of this limit. That's my expansion. What does it say? It says for every possible epsilon there is something, but on this occasion I choose a particular epsilon, and I added the index 1 to distinguish it from this epsilon. So for one choice of epsilon, 1, which I choose to be delta, for this choice of epsilon, definition of this limit tells me that there is an index n such that past that index, I have this distance of xn sequence from the A point less than my epsilon 1 chosen to be delta. Again, this 1, I just indexed my epsilon with 1 to distinguish it from this epsilon, for which we chose delta. And now we just say that that is, for this positive epsilon, look at this. What I'm saying is this now. For this positive epsilon, I can say there is an index, this index, which we built in two-stage process. First we build delta, and then we build n, basing on that delta, such that for every n after that delta, after that index, this is true, and by implication, this is true as well. It's from here. Right? If you take xn, which is close to a by the distance delta, then f of xn will be to b, close to b by the distance delta. By the distance epsilon. And here's another epsilon delta version of a definition for the limit, but now different sequence. Sequence f of xn. Look at this. For positive epsilon, I presented the place after which my sequence, my new sequence, f of xn, close to b by epsilon or less. That is the definition of the limit of my new sequence. And that's a forward proof. Look at this. I chose any possible sequence with this condition, and I concluded that for this sequence, newly built sequence, f of xn, satisfies this condition. That's the end of the forward proof. Let's just look at the opposite one. This one more challenging. The opposite one, I will do this by contradiction. So now we assume we need to prove that if we have this statement, then this one is also true. By contradiction, I'll do it like that. What do I do by contradiction? Too many lectures this week. Yeah, we will assume that this is true, but this one is not true. So we will assume that limit of f of x is not equal b, according to the definition of the limit, and yet we have this statement that for every converging sequence to a, f of that sequence converging to b. That's my assumptions. So we assume that, do I have it here? I'll bring it up a little bit. We assume that limit of f of x not equal b, but at the same time, limit of xn equal b for every sequence converging to a. That's the setup of the proof by contradiction, and I want to come up with something wrong. I want to come up with a contradiction in this setup. Look at this, what I'm going to say. I'm going to interpret what happens when limit not equal b. When limit equal b, it sounds like this. For every epsilon, there is delta such that as long as distance to a is less than delta, distance to b is less than epsilon. Opposite of that, logical negation of this statement will sound like this. There is a positive epsilon, which I will call epsilon naught. Oh, I opened the wrong. How come? There's a positive epsilon such that for every positive delta, there is always an element which on one hand closer to a than delta, but on the other hand far away from b, at least at the distance epsilon. This is the negative of the definition of the limit. And I'm going to use this to come up with a contradiction. Look at what I'm going to do. I'm going to choose a particular, because it works for any delta. I mean, this nicely, well, this is this good or bad epsilon naught. It works with every delta, so I make a choice for delta, like this, 1 on n. Just never mind this. It will come up eventually. Let me just close this. Oh, as if it's not there. I'm going to choose a particular delta, like this. For this delta, this line claims that there is an element, which this time I will denote with the index n, because for different deltas, different element. That's why I reflect this dependence, x sub n, such that on one hand, this is true. It's exactly this statement. On the other hand, this is true. And we're almost there. We're almost at the contradiction. Look at this, because I can say now, on one hand, this constructed sequence is such that, well, the distance doesn't exceed n. On the other hand, it's non-negative, so it's a by sandwich principle. I can say that the limit of these numbers is 0, which is by equivalence theorem limit of xn equal a. It's on one side. On the other side, I can say that because this distance is bigger than epsilon naught, the limit of the f sequence is not equal b. Because for limit to be b, this must also go to 0, and it doesn't because of this epsilon. And that is my contradiction. Look at this. I started with the assumption that limit doesn't equal b, and I constructed a sequence which violates this part of the contrary assumption. I constructed a sequence which on one hand converges to a, but on the other hand, f of that sequence does not. And that's why this opposite step is also true. Okay, I guess that's the hardest proof of all I presented this week, but it's Friday, why not? Now we deserve a break, right? But well, in 20 minutes we deserve a break. But that's the hardest one this week, trust me. You will have example just in a minute. You will have an example just in a minute. You need to ponder over this proof a little bit. It's hard to absorb this proof at just first time you see it, especially in class, on the time constraints and everything. But it's not an easy proof, but it's the first proof which heavily, obviously you enjoy the proof. Well, I can see that this proof caused lots of thinking, which is a good thing. Like I said, it's hard to absorb and completely, understand every bit of that proof in one go, especially in class. You need to sit over it and just spend some time with it, and then it will be absolutely clear, I'm sure. I have one example. I have two examples. These are two functions. Here's two functions. Actually, I have it on my dynamic slides. Here it is. It's the first function. Well, the function is not defined in the origin. You can't really do, because if you put 0, 0, it will be 0 at the bottom. You can't divide by 0. However, we have to, it's not set in print here, but what we meant to show here is that function doesn't have a limit when x approaches 0. And we can do it via this theorem we just discovered with you. We can do it by, remember, the theorem said function has a limit, b or any other value, when the same limit come up across any sequence which approach the point of the point A. In this case, point is 0. So for this sequence, look at this. For this function, if I take this sequence of points which approach origin from on the x-axis from the right-hand side, which one is this one? If I take this sequence, which approaches origin on the horizontal level, if you compute your function on this particular sequence, it will be 0. And therefore, the limit across this sequence will be 0. On the other hand, if I take another sequence, it's just what I said, the limit across this sequence will be 0. If I take another sequence, like this, it's another choice of a sequence. Here it is. Along the bisector, here it is. If you take a sequence by bisector, the limit, the same limit of the same function, but over the different sequence delivers 1/2, right? Just sub in 1 on n across this one, it will be 1 on n square, and it will be 1 on n square plus 1 on n square. It's double of 1 on n square. It's exactly what you see here. It's 1/2. So across two different sequences, function delivers two different limits. According to the theorem we just discussed with you, such a function cannot possibly have a limit at the origin. Because if it does, it must have limit across every possible sequence identical to each other. And this time we have observation of two different limits across two different sequences. That's how you disprove that the limit exists in the point. You try to come up with two sequences which deliver different values. Like I said, the other way it's hard because you can't check every sequence for the limit. So when you go the other way, when you prove that the function has a limit at the point, you have to go via inequality of some sort. At my first example today, remember there was this inequality between g of fn1 and g of xy0. My first example today. But when you disprove, that's how you disprove, based on my theorem via sequences. Here's another example. This function. Again, for this function, in the origin, you can come up with two sequences which deliver different values. And that's why in the origin, function doesn't have a limit. Look at this. First sequence I suggest is this. Let me just open both of them at the same time. Yeah. If you take the one approaching to the origin from the horizontal direction, then function is always 0 in that sequence, and that's why the limit is also 0. If you try the bisectorial approach, as in my previous example, I didn't do it here, but look at this. If you take bisectorial example, 1 on n, 1 on n, what happens here? Look at this. Let's just try to compute it from the top of our heads. If I compute here, we can compute it here. If I compute it here, 1 on n, 1 on n, it will be 1 on n cubed, right, in the numerator. And the denominator, it will be, well, it's not the denominator, 1 on n squared plus 1 on n4. I put them around. I mean, for the numerator, you have 1 on n cubed. x4 gives you 1 on n4. And y4 gives you, this is the value of the function on the bisectorial approach. So this is the value of my function on 1 on n, 1 on n. So if you take bisectorial approach for this function, this one, what would be the limit of this sequence? What your experience from the first year tells you. Right? What's the limit of this sequence when n goes to the infinity? I'm sorry, this equal sign is missing, of course, here.
It's 0.
It is 0, thank you very much. It is 0.
But then you're looking for something up than 0.
That's right. I'm trying to justify my choice of quite non-trivial approach here. If you choose the approach as in this example, if you choose the bisectorial approach for this function, it doesn't work. Because if you take the bisectorial approach here, it still gives you 0. That's not enough evidence for concluding that limit doesn't exist. But if you take approach along the parabola, if you take this approach, 1 on n square, and if you do computation for this approach, that's how function will look in this case. And that is 1/2 again. So this time again, we managed to find two approaches which deliver different values. And that's why we can conclude again that the limit of this function when you approach 0 does not exist. Finding such limits, finding such approaches may be non-trivial task, and you may not succeed for a long time. And yet it may be not still enough evidence to conclude that the limit exists. The only evidence that the limit exists is via some sort of inequality, an epsilon-delta, well, right now we don't have any other tools, epsilon-delta argument, as in my first example today. Any questions?
Yes. So what's the intuitive way of looking for such approach that's going to deliver two different limits?
Yeah. Well, it's a nice question, but I don't have the answer for that. There's no intuitive way for looking for that.
Like, in first year you have sort of a visualization and understanding that you can actually think of something that's clearly not going to work and you put it in because it didn't work. So there's none in this kind of situation.
Well, my answer will be this. The feeling which approach to choose, it comes with experience. There are a few examples in the tutorial set, and there won't be many examples altogether for you. In those examples, you probably find all possibilities you need to know for this topic.
So, are you suggesting
you
finish all the tutorial questions?
Yes, I suggest if you finish all of the tutorial, that's a good way to put it actually, I like it. If you finish all of the tutorial questions, you will be more or less equipped well for this topic. In general, I'm not telling you the silver bullet because there isn't one. In general, proving that the limit exists or doesn't exist, it's not trivial task even for a really experienced mathematician, not a student. So it's some limits we still don't know if they exist or not. Even with the powers of computers and finding the limit, you can come up with lots of examples where the answer is still not known to everyone living on this planet, not just everyone in this class. But be sure you won't see these examples in the tutorial set or in this topic. In this topic, they will be relatively simple, and by trying a few approaches from the from your experience with the tutorial questions, I'm sure you will find some which works for you. Or otherwise, you can try some of the inequalities. Any more questions, please? Okay, if you don't have any questions, I can go probably to my main set of slides again. From this moment on, it's all sort of quite express presentation because, hello guys, thank you very much. I know you're tired, it's Friday afternoon, I'm also tired today, as much as you are. It's just only 7 minutes left to live through the lecture. I hope we can all survive. From this moment on, it's relatively express sort of presentation because the results which I mentioned on the slides, we solved them already in some other settings, but in principle they're the same. For instance, this one says the limit of a function which has vector values can be equivalently linked to the limit of component functions, something which is done for the sequences at the beginning of today's class. I mean, we saw the very detailed proof of that. Remember, using metrics, d1, d infinity. For this theorem, adaptation of that proof will work for this theorem. So if you want to really practice your ability to present the proofs, that's a good opportunity to try to adjust that proof for this theorem. The proof we just saw at the beginning of today's class. And that's the that justifies the other definition of the limit by curves. Yeah. That's why I said here, you see, I mean, I didn't create a canvas for that because the proof is similar to the one we just saw at the beginning today, sequence of limits by components theory. The same about this slide, algebra of limits. Again, I don't have a proof for this theorem, but we saw very similar theorem, the proof for the algebra of derivatives, remember? It's the proof for this. It will be a relatively easy adaptation of the proof for the derivatives, right? That's what I say here. I don't know, limit algebraic theorem. That's the one. We proved this as well, by the way. Yeah, and that's all. Well, that's the end of the limits now. Yeah. Like I said, I mean, the limits of functions, they basically rely a lot either on definition or limits of sequences, and the limits of sequences we studied quite extensively, and the limits finish here. I have 5 minutes left. I don't see the point why we can't discuss this. It's just a bunch of definitions, open, closed subsets, boundary, and interior. Again, there isn't much of the proofs here. I have one proof. Well, not proof. I have one tutorial question which I put together to show you. Well, let's just look at the proofs first. I'll decide what to do with that. Just a bunch of definitions of which you need to know to live through this topic. For instance, a point, if you have a set, or we call it a domain in Rn, some points will be classified in different classes, like a boundary point, interior point. For instance, interior point is the one which is a part of the domain together with some ball around it. So if a point comes together with a ball, if point belongs to a set together with the whole neighborhood around it, then we call it interior point. And if a set consists only of the interior points and nothing else, if every point in the set is interior, we call the set open in that case. Closed is the one which is a complement to open. Boundary point, well, I just said here, it's the one such that no matter how small you take the ball around that point, there will always be points from the set and not from the set. In that case, we call it a boundary. So boundary is the opposite of interior point, because for the interior point, if you keep squeezing this ball, at some stage, the ball will go into the set in its entirety. Whereas for the boundary, no matter how small you squeeze it, there will be points both inside and outside. And you know what? Why not just do the example? We have 4 minutes. I'll show you one example. Beg your pardon? Pushing it. You know what? Okay, maybe you're right. Maybe we shouldn't push it that far. You're right, actually. It's a quite heavy. It's not a heavy. I don't know. I don't want to waste it. Because it's a good demonstration. It's one of the tutorial questions from next week. But if I do it on Monday, it still will fit in the next week. Okay. Thank you very much for the first week. You're all free to go. Thank you.